Hello, I am Monica from ECE department. Today I would like to discuss how to maximize the gain of antenna using optimization techniques. Antenna gain plays a crucial role in the performance of wireless communication systems as it determines the ability of an antenna to transmit or receive signals effectively. The gain of an antenna refers to its ability to concentrate or direct electromagnetic energy in a particular direction. Antenna gain is typically expressed in decibels. It is used to quantify the efficiency and effectiveness of an antenna in transmitting or receiving signals. To optimize the gain of an antenna, we have various techniques and algorithms. In this presentation, I have used golden section method as an optimizing algorithm for maximizing antenna gain. The gain formula can be obtained from the basic definition of gain, that is it is defined as the ratio of radiation intensity in a particular direction to the radiation intensity of an isotropic radiator. That is, gain is equal to 10 log I of theta by I naught. I of theta is the radiation intensity in a particular direction and I naught is the radiation intensity of an isotropic radiator. I of theta can be expressed as I naught cos square theta. By substituting this, we get gain formula as 10 log cos square theta. The radiation pattern of a half-wave dipole antenna has a maximum radiation intensity in the plane perpendicular to the antenna axis. To account for this, a factor of 1.2 is typically used. So the gain formula becomes 10 log 1.5 cos square theta. By substituting the angle theta as pi L by lambda, we get the gain formula as 10 log 1.5 cos pi L by lambda whole square. This is the gain formula we obtain for the half-wave dipole antenna. It takes into account the dipole length, wavelength, and radiation pattern to calculate the gain in decibels for different dipole lengths. The objective function of the gain we used here is 1.5 n into log of n pi L by lambda square. Here L is the length of the antenna, lambda is wavelength, which is equal to c by f. C is the speed of light, f is frequency. In general, n could represent a scaling factor or a parameter that is chosen based on design requirements, antenna type, or other factors. The range of n would depend on specific application and design considerations, and it could vary from positive to negative values or even non-integer or fractional values, depending on the requirements and the characteristics of the antenna. The limitation of antenna is it is important to note that the formula may not be valid or meaningful when the length of the antenna is zero. In most practical antenna designs, the length of the antenna is a critical parameter that determines its performance characteristics, including gain, radiation pattern, and impedance. When the length of the antenna is zero, it is essentially means that there is no physical antenna element present, and therefore the concept of gain may not be applicable. The steps of the golden section search. We need to maximize our objective function f of x in the interval a naught comma b naught with some uncertainty. The formula 1 minus rho whole power n less than or equal to uncertainty by upper interval minus lower interval, that is b naught minus a naught, gives us the number of iterations n. In iteration 1, we would like to find 2 points a1 and b1 between a0 and b0. a1 can be obtained by the formula a1 equal to a0 plus rho times b0 minus a0 and b1 equal to b0 rho times b0 minus a0, or from the formula b1 equal to a0 plus 1 minus rho times b0 minus a0. Here rho value is equal to 0.38. After calculating a1 and b1, we have to find the value of our objective function at a1 and b1. If f of a1 is greater than f of b1, our new interval will become a0 comma b1. If f of a1 is less than f of b1, our new interval will become a0 a1 comma b1 b0. In iteration 2, we find a2 and b2. The a2 can be finded from the equation a2 equal to a0 plus rho times b1 minus a0, and b2 is almost equal to a0, or it can be found from the formula a0 plus 1 minus rho b1 minus a0. Again, we have to calculate the objective function value at a2 comma b2, and we have to compare and find new intervals, and we have to repeat this process up to n intervals. Uh, Golden section search for maximizing gain. The objective function is gain equal to 1.5 into n into log cos n pi L by lambda whole square. We have to maximize the gain in the interval 0 to L. This is the Python code to find the maximum gain of an antenna using golden section search algorithm. Firstly, I am importing three libraries, mat, numpy and matplotlib. This def gain will return the gain value. That is, it calculates the gain equal to 1.5 into np dot cos np dot pi into dipole length by wavelength power 2. Here C is the speed of the light 3 into 10 power 8. F is the frequency of 1 into 10 power 9, that is 1 gigahertz. Wavelength can be calculated by C by F formula. By running this code, we will get the gain at particular length. Here initially I have taken minimum length as 0 and maximum length as 100. That is, we have to maximize our function in the range 0, 100. Here left equal to minimum length, that is A naught is equal to our minimum length and B naught is equal to our maximum length, right. Uncertainty I have taken as 10. Rho value is equal to 3 minus root 5 by 2. This n will return the number of iterations our code has to run. This for loop will run for n iterations. For suppose for the first iteration, here it calculates a1 equal to left plus row into right minus left, that is a naught plus row times b naught minus a naught. Here in first iteration it calculates b1, that is equal to b naught minus row times b naught minus a naught, and it calculates the gain value at a1 and b1, and it will repeat up to n iterations. Finally, it will compares the gain at two values and updates the new interval for every iteration. This is the code to plot the gain. On the output we have got is the maximum gain is 1.5 at the length 60. The last interval after n iterations is 52.7864, 67.376. The plot is obtained here. It is a gain versus length. We have obtained the maximum gain at this point. These are the references used in this presentation. Thank you.